Hi everyone, and welcome to our live stream for the first chemistry paper. So what we're going to do tonight then is we're going to go through everything that could come up on the first chemistry paper, so that's units C1, C2, C3, and we'll cover both the combined science and triple science, higher and foundation. So what I'll do is I'll try to flag those up as we go, and I'll also try to point out any of the bits that are on the advanced information, but as we found out from the biology paper, everything's coming up anyway. So what we actually do know from that one, if they follow the same pattern with chemistry, then higher tier folks, I would say you can kind of guess to about 75%-ish of the questions are going to be advanced information, which still leaves 25% of the marks that weren't really on there. So we are going to try to go through all of this. As I say, I will definitely spend a little bit longer on those practical tasks, particularly the separating mixtures bit, as they seem to have gone overkill on the advanced information with those bits. But we will cover everything. So let's make a start then. As I say, you can post any little questions in the chat window. I will try and get to them, but obviously bear with me because there is a bit of a lag between what I say and when you actually hear it. Let's start off then with C1. Now C1 is lovely and short. What we're really doing here is looking at particles to start off. Now, one of the key things that we know about chemistry is that we're talking about things we can't actually see in the best detail in the lab. So when we talk about particles, these are far too small for you to actually be able to see with your naked eye. So instead, what we do is we use these things called models. Now, a model in science is what we're going to use to try to solve problems, to make predictions, and to try to develop better scientific understanding. So what we're really going to be able to do by using a model of our particles, known as the particle model, is we're going to be able to describe the arrangement of those particles and how they move in the different states of matter. So what we actually know then, hopefully from Key Stage 3, are that when we're talking about states of matter, there are three: solid, liquid, and gas. So what we can do with the particle model is that we can actually explain certain properties of solids, liquids, and gases. Our first property we need to be able to explain using particle model is the ability to compress things. And the only one we can compress is a gas. The reason for that is that you've got space between the particles. So hopefully this bit looks quite familiar to us. These are the typical little drawings that we have of the particle model. And when we look at the gas, you can see there are spaces between them. If you look at the solid and liquid, there's no gaps between those particles, therefore you can't compress it. In terms of the ability to flow, then what we'll find is that solids cannot flow, whereas both liquids and gases can. Reason for that, particles are in a fixed position within the solids, whereas in liquids and gases they can move around themselves. In terms of the particle model itself then, what we need to know is how to draw those little diagrams that I've just shown you, and you need to know the arrangement, the relative distances between the particles, and how they move. So for our solid, first of all, they are arranged in a regular pattern. They're lovely nice straight lines. They're very close, i.e. all touching, and they just vibrate very gently around a fixed position. For liquids, it's a random arrangement. They're close together and they're able to just move around each other. And in the gas, random arrangement once more, they're far apart and they move really quickly in all different directions. So when we're using our particle model, one of the things that we can do, obviously the 2 dimensions that we've already seen, but we can also draw them in 3 dimensions, still showing each of those particles as those little circles basically. The downside of drawing in 3D is that there are some of those particles that are actually hidden from view, either completely if they're in the middle, or partially if you can just see a little edge of them. So that might lead to a bit of a misunderstanding there. Next bit is the different changes that we can encounter in chemistry. We have physical and we have chemical changes. A physical change is just a change in the state of matter. So solid, liquid, gas, when they're changing between those, that is a physical change. 2 key points about our physical change. First of all, they tend to be reversible. And secondly, we are not making a new substance. If we have ice made of water, obviously, when we melt it, still water. If we evaporate it, still just water. So no new substance made, reversible in terms of the ability to go from solid to liquid to gas and back again, and it's just a change in the state of matter. Chemical changes then. These are the ones where we're going to produce one or more new substances as the result of a chemical reaction. So because of this, they tend to be irreversible, so we can't get our initial reactants back, and the products are actually going to have quite different properties to those of our original reactants. So we've got those two key types of change that we could be asked about. For those of you doing higher tier, either triple or combined, you also need to know some of the limitations of the particle model. Because where we are talking about using these little models to represent our particles, it's not perfect. And there are three kind of key limitations, if you like, to do with the particle model. First of all, we don't have anything taken into account to do with the forces between those particles. Secondly, the size of the particles really isn't that representative. And thirdly, we're not really representing the space between the particles accurately. So those are our three kind of key limitations that we've got here. If we think about how particles are actually held together, the phrase that we are going to use probably to death in this topic is electrostatic forces. We have electrostatic forces of attraction between positive and negative charges. The further apart those charges, then the weaker the forces will be. Back for everyone, so foundation, higher, combined, triple, absolutely everyone in the world doing chemistry tomorrow. We now need to know a little bit about atomic structure. First thing, let's learn some key terms and what they actually mean. So element, first of all. This is a substance whose atoms have the same atomic number. They're the things you'll find on your periodic table. Remember, you get one of these in the exam. It's the one that says data sheet on the front. Turn it over, you find the periodic table. All you will find on a periodic table are elements. If you're looking at a compound, a molecule, anything like this, you're not going to find it on there. So don't waste your time looking for things like water or carbon dioxide as they are on the periodic table, because it's only elements, folks. When we talk about an atom, this is the smallest particle of an element, and molecules are particles that consist of two or more atoms that are chemically joined together by those bonds. They can ask us about the size of our atoms here. So what we need to know is that the atomic radii and bond lengths are typically around 10 to the power minus 10 meters. So this comes up as a little estimate question every once in a while. So the key bit to look for is times 10 to the power minus 10 there. That's what you'll be looking at. If we now consider the structure of an atom, this should be a very familiar diagram to us all. This is what we now know as the structure of the atom. So in the centre here, we've got the nucleus, which is made up of protons, the ones with the pluses on them, and our neutrons, the little pinky coloured ones. And then around the outside, in these things called shells or orbitals, we find our electrons with the little negative sign there. You need to know the structure of the atom. Sometimes on the foundation paper particularly, they do like to give you a little question asking what X is with a little label going to that diagram. And the one thing that they really like is the table about the subatomic particles, their relative mass and their relative charge. So we've three subatomic particles: proton, neutron and electron. The proton, relative mass is 1, relative charge +1, proton positive. Neutron, relative mass is 1, relative charge is 0, neutral. The electron has a relative mass of 0.0005 or 1 over 2000 and a relative charge of -1. That little table pops up every once in a while where you then need to just fill in the blanks. So make sure you do know those bits for the three subatomic particles. Now, going back to our periodic table here, what we actually have are not only the name and the symbol for each element, but there are two numbers in each of those little boxes. One of them is going to be your atomic number, the other is your relative atomic mass. Now OCR are super nice because if we look at this bit right here, and this is the exact data sheet you get in the exam, it's a key. This literally tells you which number is which. So no excuse for getting this wrong on the exam. It's printed right there. You can just read it, folks. So when we're talking about the atomic number, that's going to tell us how many protons or how many electrons there are. They're the same in an atom. So whatever the atomic number is, read it off, write it down. That's your protons or electrons. To work out your number of neutrons, we need the mass number, because your mass number tells you protons plus neutrons. So if we want to work out how many neutrons there are, mass number minus the atomic number, and you've got it. The only one to watch out for there is if they've given you an ion. Now an ion obviously has a charge associated with it. The only thing that's going to have happened is electrons are going to have been gained or lost. So your atomic number is still going to be your number of protons. Your number of neutrons is still mass number minus the atomic number, but to work out your number of electrons, you've got to look at the charge. If it's a negative, however many negative charges there are, add that onto your number of protons. If it's a positive, take however many positive charges there are off your number of protons, and you've got the electrons then. Another key term they like is the word isotope. The definition for an isotope you need to know is the element with the same number of protons and electrons but a different number of neutrons. We could phrase that a different way. We could also write that the atomic number is the same but the mass number is different. So if they're asking you to define isotope, either of those two will work for the marks there. As we mentioned, ions are these charged particles, and if we're talking about a negative ion, it's gained electrons. Positive ions have lost electrons. Last bit of C1 was looking at those 4 key scientists who actually came up with this whole structure of the atom for us. You don't need to know the years, you don't need to know their first names, just know their surnames and kind of their key discoveries if you like. So Dalton is first. He said atoms are tiny indestructible spheres. All atoms of an element are identical, but different elements contain different types of atom. Number 2 is Thomson. He was the one that discovered the electron. Carried out these experiments called cathode ray experiments, fired beams, and what he actually found was these must be negative little particles within these beams. So he said that's an electron, and he came up with this idea that he called the plum pudding model, i.e. we have this big positive cloud with these little negative electrons dotted around in it, like a plum pudding. Scientist number 3 is Rutherford. Now, Rutherford was the one that did the gold foil experiments. So he fired these alpha particles at these thin sheets of gold foil and watched what happens. Had it actually been accurate that the plum pudding model was true, those alpha particles would have just gone straight through. They didn't. They bounced off in all different directions. So he explained that by saying there is a nucleus at the centre here that's positive and it contains most of the mass. And the electrons orbit around that nucleus kind of like planets. Final scientist is Bohr. He used mathematical models just to show that those electrons actually occupy these fixed energy levels or shells around the nucleus. So that is the entirety of Unit 1. On to C2 then, and yes, Mendeleev is the guy that developed the modern periodic table as we know it. The first thing we need to know about in C2 then is how to calculate relative formula mass. When we're talking about these relative masses, we have the relative atomic mass, what we see on our periodic table, which is the mean mass of an atom of an element when it's compared to 1/12 the mass of an atom of carbon-12. Delightful mouthful. And the relative formula mass is just when we add up all those atomic masses in the formula. So realistically, it's an adding exercise. If we've got, there we go, so here's a little chemical formula for us. We've got magnesium hydroxide there. What we need to do is understand how many of each atom are present first of all. So because we've just got the Mg on its own, there is one magnesium, but because the oxygen and the hydrogen are in brackets with a little 2 after them, that means everything in brackets is times by 2. So 2 oxygens and 2 hydrogens. So what we do, grab the periodic table, then you're going to be able to look up magnesium, which is 24.3. We've then got our oxygen, which is 16, and we've got our hydrogen, which is 1. What we then do, add it all together, and you've got your relative formula mass, okay? So look up the relative atomic masses on the periodic table, and then all you got to do is just add it together using your calculator. As I always tell my year 11s, please stop trying to do mental maths. You don't have to. That's the purpose of a calculator. In an exam, you're likely to be, well, more likely to make mistakes that are quite silly because it's a stressful situation. So don't risk it. Use a calculator. Next, empirical formula. When we talk about the empirical formula, this is quite simply the simplest ratio of all of the atoms in a compound. So if we've got, let me just pick one here, let's do this one. So let's do C6H12, okay, so that's not the empirical formula. To get the empirical formula, what we need to do is find the highest common factor of both 6 and 12. So highest common factor of 6 and 12 is 6, so 6 divided by 6 is 1, 12 divided by 6 is 2, so what we actually have as the empirical formula is just CH2. Once you've found that highest common factor, divide each by that, and it tells you then what number of those particular elements you've got in your final empirical formula at the bottom there. So you can see CH2. That's all you've got to do. It's literally highest common factor, divide the chemical formula by the highest common factor, write it down. Now, on we come to the start of the huge chunk of advanced information bits. We're going to be looking at basically mixtures, pure substances, impure substances, how we separate them, how we identify if they're pure or not. When we're talking about a pure substance, that consists of a single element or a single compound. Impure substances, more than one element or compound. What we find is that they're going to probably, looking at that advanced information, give us a question about separating a mixture of things. Now, when we talk about a mixture, that's one element or compound mixed together with another that's not chemically bonded there. So, air, for example, the air you're currently breathing in is a mixture. There's nitrogen, oxygen, etc. They're not chemically bonded to one another. They are just present within that same space together. Another mixture that you are going to see coming up again in paper 2 chemistry are alloys, which is a mixture of a metal with one or more other elements. So how do we work out if we have a pure substance? Simply, we melt it, because the melting point is going to tell us whether it's pure or not. If it melts at a single temperature, it is pure. If it doesn't melt at a single temperature, it melts over a range, it is impure. So how do we work that out? You get your substance, you heat it up. If it all melts at one temperature, pure. Doesn't melt at a single temperature, but bits are melting, there's bits left over, it's impure. Now, on to our techniques for separating. So this is listed in those practical bits there. So as I say, it wouldn't surprise me at all if there was a question worth a reasonable number of marks here, where they're going to give you a selection of the different substances in a little table, giving you some key bits of information like their melting points, boiling points, where they're soluble or insoluble, and ask you to separate them all out. Could even be a 6-mark question. I think it was on the practice papers all those years ago that they actually set that as a 6-marker. But to the best of my recollection, it's never made it onto the real GCSEs. Maybe this is the year. So, first one, we're going to be having a look at a load of words that we need to understand before we can go on to the idea of filtration. If we talk about a solution, that is the solute dissolved in the solvent. The solvent is the liquid that actually dissolves the solute. Solute is the solid that dissolves. If something is soluble, it will dissolve. Insoluble, it will not dissolve. So technique number 1. Don't mind me just dropping my whiteboard. So technique number 1 is our filtration. So what we can see here then is the setup for filtration. This is what we're going to use to separate an insoluble solid from a solution. So think sand and water, for example. What we've got, bit of filter paper in our funnel at the top, place it in a conical flask, pour the mixture at the top. The insoluble solid is going to be left as the residue. The rest comes down into the bottom of our flask as the filtrate. So what we'd find is if they give you something and one of those bits is insoluble and the others are soluble, then we're going to obviously add water to dissolve it all. Then we're going to pour that through a bit of filter paper to separate out our residue, the insoluble part. So what we actually find then is that's going to let us separate out one of those parts. It is worth saying that you should rinse it and then dry it to make sure it is truly pure. Second technique is going to be crystallization then. So crystallization is what we're going to use to separate a dissolved substance from the solution. What we've got here is the evaporating basin at the top. We sit it on top of a water bath, so a little beaker filled with water that we are going to heat. You don't heat the evaporating basin directly, otherwise all that's going to happen is it's going to start spitting out the chemicals all over the shop. So we use the water bath because it allows us to then heat it a little bit more gently and safely. The way this works then is as we heat it, then the solution is going to evaporate from that basin. Now what that means is we're going to actually saturate the solution in the evaporating basin. At that point, no more solute can dissolve at that temperature, so we start to see little crystals beginning to form. So what we then find is we turn the heat off, let it cool down, because as the solution cools, what we actually find is that we are going to be able to then get more crystals coming out. So what we can do once we've actually carried this out, filtration just to remove any of those crystals from the remaining solution, and then we just dry them in a warm oven. We do need to be polite in the chat, folks, otherwise I will just start blocking some people. Technique number 3, simple distillation then. What we've got here is the ability to actually separate a solvent from the solution. So obviously be mindful of the fact that if we're using crystallization, the solvent is just going to be lost to the surroundings. So if the question is asking us to separate all of those chemicals to have pure substances left, that's not going to work because one of those substances would be lost to the surroundings. We can use simple distillation because what we can do here is, as we heat up in here, then our solution is actually going to have the solvent evaporate, and then it's going to condense as it passes down the condenser. Because what we've got, cold water goes in, and then it's going to change our vapour to a liquid, which we can collect at the other end. Now, that means that we will have the solvent over here, and the solute will be left in the actual beaker here. So what we've actually got is a way to separate out all of those there. Now, we do have another option. We have fractional distillation as well. So fractional distillation is what we will use to separate 2 or more substances that are in the liquid state. Key thing, they've got to have different boiling points. This bit of equipment here is the fractionating column, and that is one of the things that they can ask you. Literally, I'll just have a little line here with what is X, and fractionating column is what we're looking for. Now, fractional distillation is something that we mention here in terms of we can separate out 2 liquids that have different boiling points. But what we also find is that you're going to see this coming up in more detail in the Unit 6 when we look at crude oil as well. The last separating technique is chromatography. Now, chromatography is going to be how we're going to separate out generally coloured things. That's going to be the most likely setting on your exam paper. So think paints, inks, dyes, anything like that. Chromatography is going to be the go-to. We've got a couple of different options for chromatography. We have got paper, thin layer, and we've got gas chromatography. The general setup for paper and thin layer chromatography is the same. What we have is some kind of a tank that allows us to stand our stationary phase. Now this stationary phase could be the paper, if it's paper chromatography, or the TLC plate, which is basically a bit of plastic or glass with some silica or alumina powder on the surface. What we do is, a couple of centimetres up from the bottom, we draw a pencil line. Must be pencil because pen will run. We then put a little spot of our sample onto the pencil line. We place it in our little tank here, making sure the solvent doesn't reach the sample itself. We then leave it, and what's going to happen is the solvent's going to move up the paper or the plate, and it drags that sample with it as it goes. We take that out just before the solvent reaches the very top there, and then we can work out how far it's moved. There is a calculation with this. The calculation is called the RF value. Now, the RF value, quite simply, to work that one out, is distance travelled by the substance divided by the distance travelled by the solvent. Now, when we're doing this, first point, you need a ruler. So take a ruler into the exam with you. And what we're going to see is we are going to have potentially something that looks a bit like this. Now, on here, what we can see is we've got our solvent front. The solvent front is literally where the solvent gets to at the very top there. We then have these different little spots that are going to be our different substances. What you need to do is measure from the baseline, so where we started, to the center of that spot. Okay, so what we need to do is just go careful with measuring. Don't go to the top or the bottom. Try to measure nice and vertically from this line to the center of the spot. Then to calculate your RF value, distance travelled by the substance, so this bit, divided by the distance travelled by the solvent, so baseline to solvent front. Stick it in your calculator again and you will get an answer. Now, the other type of chromatography is gas chromatography. In terms of our gas chromatography, this is our setup. We have got a carrier gas, which is just unreactive gas. We're going to inject our sample here. The carrier gas then pushes it through this coil, which is filled with our powder, so the stationary phase, the silica or alumina powder, and then it's going to come out and be picked up by the detector. As those samples make it through, the computer then gets a little peak on the screen wherever a sample is detected. Now, what we actually find then is we've used a couple of key terms here: stationary phase and mobile phase. You need to be able to identify the stationary phase for paper, thin layer and gas chromatography, and the mobile phase for each. So, stationary phase is the bit that doesn't move. The paper, the silica or alumina on the plate, the silica or alumina in the coil. The mobile phase, the bit that does move, so that will be the solvent in paper and thin layer chromatography, or the carrier gas in our gas chromatography. So what we've actually got is the ability then to separate out a whole range of different substances. You're not going to be using gas chromatography to separate any mixtures that they're going to give you on the paper. They could ask you obviously how it works, but it won't be any part of how would you separate this mixture of chemicals. That's going to pretty much come down to your filtration, crystallization, distillation setups. Think about the sequence and then you should be able to explain it. In terms of what we use chromatography for then, it allows us to actually identify whether a substance is pure or not, first of all. If it's pure, single spot. If it's impure, there'll be more than one spot. Now, the other thing they can do is ask you to identify which substance actually matches another sort of year or a pen or a paint sample, something like this. So what you've got to do there is you will have a selection of different little spots, and they will literally say if this one is our sample labelled S. Here we go. So sample labelled S, this is what we're trying to work out where it came from. You've then got two others. All we need to do to identify which one it comes from, match the spots. It's literally a spot the difference. If they're different, it's not that. If they're the same, we found it. So in this case, our sample is the same as the one on the right. So whatever that was would be the correct answer there. How do we know? Because the spots are in the same place. Don't overthink it, that does the job. Now, you could be asked to compare thin layer chromatography with paper chromatography. The reason thin layer chromatography is better is because it's quicker, it's more sensitive, so we can use much smaller samples, and a single spot from that TLC plate can then be removed for gas chromatography later on. So I would try to remember quicker and more sensitive as two kind of go-to answers for why TLC is better than paper. Now, when we actually come on to the next part, we're starting to think about bits on the periodic table to an extent. We're going to start thinking about metals and non-metals. Now, as far as the periodic table goes, hopefully we remember the metals are on the left, the non-metals are over here on the right. We do need to know a few key features here. First of all, physical properties. These are the characteristics we can observe or measure. Things like whether it's malleable or brittle, whether it's ductile or non-ductile. Chemical properties are ones that we can only determine by looking at those chemical reactions. So this is things like metals and non-metals reacting with oxygen to form an oxide. The metal oxides producing an alkaline solution if they're dissolved in water, whereas non-metal oxides produce acidic solutions. So what we've got are just some of those little bits that we can pull out only through chemical reactions. You can't get that just from looking at it. One thing to bear in mind when we're talking about the periodic table is we've got these vertical columns, those are our groups, and the horizontal rows are the periods. OCR are again very nice to you here. Notice these numbers in brackets at the top. Those are your group numbers. So they've literally put it on the periodic table for you. Group numbers are literally at the top in those brackets. Period numbers, however, they've not written on there, and this is where people make silly mistakes. Why? Because a lot of people say this is period 1, missing hydrogen and helium. Hydrogen and helium are the first period, lithium etc. is the second, sodium is the third, and so on. They have asked questions in the past where they've given basically a little outline of the periodic table with key ones on there, and what they've then asked you to do is to basically identify something in group 2 period 3. That doesn't mean pull out the periodic table at that point. Reason is because that's not going to have the same as their little sample they've given you. You need to just use the ones printed in the question for that, okay? So if they've given you a little outline of the periodic table with only some elements on there, so they will have put on, say, maybe lithium and another one over here, for example. So if you've only got a couple of little samples on there, don't then pick any element from the periodic table. Pick one from the actual question itself. So just watch out for that, because some people fall into that trap. In terms of how we actually have structured our electrons then, what we have is the electrons are arranged in shells around the nucleus, as we've already said. Now, the electronic structure just gives us a way to describe how those electrons are arranged. One phrase we should know is the outer shell, which is the outermost electron shell. Okay, so it's the furthest from the nucleus with electrons in it. Okay. There are basically 4 rules to remember as far as the number of electrons we find in each shell. First shell can hold a maximum of 2 electrons, second and third up to 8, and the fourth, GCSE level, shove anything else that's left over. Can hold up to 18, but we're going to just learn it as the rest. So what we actually find then is if we're asked to work out the electronic structure of something, look at the periodic table, find the atomic number. So let's just do magnesium, for example. That's got an atomic number of 12. So what we then have is, in the first shell will be 2 electrons. Second shell, that can hold up to 8. So all 8 go in there. and then our third shell has 2 electrons. So that shows us our electronic structure for magnesium. Now, if we're going to write that out numerically, then it will be 2.8.2. That little way of writing those numbers there actually gives us a lot of information, because this last number here tells us the group it's in. So the last number, so the number of electrons in the outer shell, that is the same as its group number at the top in brackets. The number of numbers we've got, so in this case we have 3, that is the actual period it's in. So this is in period 3. And if you add them together, then obviously we have the atomic number. As we mentioned earlier, we have these things called ions, which are charged particles. So a charged particle is just one that either has a positive or a negative charge. And the reason, because it's either gained or lost electrons. However many electrons it's gained or lost is the charge it then has. Those ions are then going to be attracted to ions of the opposite charge. So this is where we come into our first bit of bonding, and we're going to look at ionic bonding. Now, if we're asked to show ionic bonding, what we need to do is work out what is happening. So I'm just going to start with lithium because it's a nice small one, and we're going to look at fluorine again because it's got a nice low number of electrons for simplicity of drawing today. What we're going to do is draw a dot and cross diagram. Okay, so a dot and cross diagram, quite simply, has one of the actual atoms with dots and the other with crosses. Hence the name, dot and cross. Now, what's going to happen to form an ion is this electron is going to be transferred from the metal to the non-metal. So what we then form is a lithium ion, and because it's lost 1 electron, it has a single positive charge, and we get a fluoride ion which has gained 1 electron, therefore it has a single negative charge. So what we're going to do is just show that electron as a cross, because it started with lithium where it was crosses, therefore when we draw it in fluorine it must be a cross as well. So just go careful to make sure that you don't just randomly change it to a dot. Stick the square brackets around it and the charge you get on the outside there as well. Now, when we're talking about ionic bonds, these will form between a metal and a non-metal. So wherever we see a metal and a non-metal, that is going to be ionic bonding. Now, ionic bonds are strong electrostatic forces of attraction between those oppositely charged ions. We then come on to our simple molecules. Simple molecules, quite simply, are small ones like carbon dioxide, oxygen, etc., made of only a few atoms, and they're joined by covalent bonds. Now, a covalent bond is a shared pair of electrons. So if ever you're asked what is a covalent bond, shared pair of electrons is all we need to write for that. These will form between non-metal atoms. So covalent bonds between non-metal atoms. If we have a look at the simplest one, we can just do hydrogen. And again, drawing the dot and cross diagram, only the outer shell's needed here. And all we need to do is make sure that any of the electrons being shared are in that little region between the 2 shells. Okay, so we can see we've got 1 shell for 1 hydrogen, shell for the other hydrogen. They have 1 electron each. They're shared to make a covalent bond. That is our shared pair of electrons. Covalent bonds themselves are strong bonds. They are electrostatic forces of attraction between the nucleus of each of those bonded atoms and the shared electrons. What we do find is in simple molecules, small molecules, we have these weak intermolecular forces, and this is why they tend to be gases at things like room temperature, because if they've got very weak intermolecular forces, that means it doesn't take much energy to overcome those, and therefore they become a gas. If we think about our covalent structures then, we can form what we refer to as a giant covalent structure. So giant covalent structures, quite simply, are ones with many non-metal atoms which are joined together by those covalent bonds in this regular repeating pattern. That's going to be a lattice. So anytime you see the word lattice, it's just a repeating pattern. Giant covalent, that just means that it's many of these joined together by covalent bonds, shared pairs of electrons. Next chemical type are the polymers then. Now, polymers are made from many monomers joined together. And in order to do this, we need high pressure and a catalyst. And this is addition polymerization. Comes up here, comes up in Unit 6 as well. Now, in terms of how we name a polymer, dead easy. Whatever they've told you the name of the monomer is, copy it and then write the word poly in front. If they ask you what the name of a monomer is from a polymer, then just read whatever the polymer name is and then just literally write down everything except the word poly. If they ask you to draw the displayed formula for a polymer, then they will give you a monomer first of all. So if we just do a quick monomer here, there's our monomer. Now, your monomer will always have a double bond in the middle. If they ask you to draw the displayed formula for the polymer, quite simply, all we're going to do is copy it, changing the double bond for a single one, sticking it in brackets, arms out the side, and a little N in the bottom corner. So really straightforward here. Whatever they've given you as the monomer, copy it, swapping out that double bond for a single, little arms out the side, in brackets, and don't forget the little N in the bottom corner there, which just stands for many. If they give us the polymer here and ask you to draw the monomer, reverse that. Copy it, ignoring the bit sticking out the side, and then change that single bond for the double. Job done. In terms of the properties of our polymers, we get different properties based on how they're actually joined together. So some of our polymers are actually quite easy to separate from the individual strands because they're not cross-linked. So those individual polymer molecules are just having these weak intermolecular forces of attraction between them, so minimal forces will overcome those. If we've got one with cross-linking, like our thermosetting polymers, they have cross-links that hold all of those individual polymer chains together, and therefore it makes it harder to separate. They're going to be more rigid and much stronger. The next material we need to know then is metals. Now, metals have their own type of bonding called metallic bonding. So if you're asked what's the bonding in a metal, metallic is the answer. They do quite often ask you to describe the bonding in metals, and this will be a 2 to 3 mark question. There's normally a little space of blank lines at the top before you get to the actual lines for your answer. Reason for that is you can draw a diagram if you wish. I always recommend drawing the diagram and labelling it because you can pick up 2 marks from the diagram alone. This one right here. You need to draw at least 6 positive metal ions and label them positive metal ions. Then stick a few little dots around, label those delocalized electrons, that's 2 marks. 3rd mark would literally be for saying that the metallic bond is the force of attraction between those delocalized electrons and the positive metal ions. Now, what we actually find then is that those are strong electrostatic forces of attraction again that hold the metals in place. Next up, we are going to talk about the periodic table and Mendeleev. So when we're talking about Mendeleev then, he's the guy that came up with the periodic table we still use today. What he did was a little bit different to others, but not overly different. He did still consider the atomic masses. So when he was ordering them, he put them in order of atomic mass first of all. But this is where he started to sort of go away from what people had done before. He then decided to group them based on their chemical reactions. So what he actually did was he started to sort them, place them into this very familiar structure we see today. And when he got to a point that thought, well, actually this one would be the next little one along based on its mass, but it doesn't really fit there in terms of its properties or its reactions. So what he actually did was he left a gap for things he thought, we've just not found this element yet. And in one case, he even swapped 2 round. What we do know is that he was spot on with what he did, because we've now discovered atomic number. So remember, atomic number is the number of electrons or the number of protons. And what we do know is that what he did there by swapping those elements around, by leaving the gaps, exactly right. We've discovered those elements that were in the gaps. We've seen that the atomic numbers actually do correlate and they count up lovely and sequentially as you go through. He was right. We do have another scientist called Ramsay, and Ramsay was the one that discovered argon, a gas that we didn't have a clue existed before that point. Then he went on to discover helium, and after that, neon, krypton, xenon. All of these are in our group 0, the noble gases. The reason no one had discovered them was because they just don't really react with anything. So no one kind of thought they were there because they didn't take part in reactions, so they were just a bit invisible really. Next bit of C2 is the carbon allotropes. Now, allotrope just means different forms of an element in the same state. So all we're changing are the atomic arrangements. We're not changing the element, we're not changing the state at all. So what we actually find is we're going to be looking just at carbon, because carbon's a bit special. It's in group 4 on the periodic table, which means it can form 4 covalent bonds. It won't always form 4, but it can form up to 4 covalent bonds. Now, those bonds could be with other carbon atoms or with different elements. We can have single bonds, we can have double bonds, the list goes on. It's a very versatile element. The first one then is diamond. So this is our first allotrope of carbon. Diamond itself is made of carbon atoms joined to 4 others. So in diamond we have 4 covalent bonds for each carbon. What we find in terms of the properties then, diamond has a very high melting point and is hard because there are many strong covalent bonds which require a lot of energy to be broken. If ever they ask you a question on the exam paper saying, explain either melting point or hardness using ideas about structure and bonding, this is the phrase to use. It has many, name the bond, which require lots of energy to be broken. Okay, so in this case, because we're talking carbon, then it has many strong covalent bonds which require a lot of energy to be broken. That's your answer. What we also find is diamond does not conduct electricity. Simple reason, there are no delocalized electrons. So if you're asked why something does not conduct electricity, there are no delocalized electrons is all we need to put. Number 2 in our allotropes of carbon, graphite. Now in graphite, each carbon atom is bonded to 3 others. So what we actually find here is we're only using 3 of those 4 possible electrons. That 4th one becomes delocalized. Now in graphite, what we end up with are these individual sheets that are then held together by these intermolecular forces. So as far as our graphite properties go, it has a high melting point because we have many strong covalent bonds which require lots of energy to be broken. It's going to conduct electricity because we do have delocalized electrons, and it's also going to be slippery. So that means we can use it in pencils and lubricants because those intermolecular forces are easily overcome and therefore the layers just slide over each other. The next one is graphene. Now graphene is basically like a single layer of graphite. It's extremely strong, it's still bonded to just 3 other carbons, so we have a delocalized electron, therefore it will conduct electricity. Now, the graphene is one that's got a lot of potential uses in the future in terms of rather quick charging batteries and circuits that are going to be incredibly thin, but we're not there yet. Watch out for them chucking it in unfamiliar contexts. So it conducts electricity because the delocalized electron is extremely strong due to the fact it's got many strong covalent bonds which require lots of energy to break. The last ones are the fullerenes. Now, fullerenes are a group of different carbon allotropes which are shaped like tubes or balls. When we talk about a nanotube, that's basically a sheet of graphene that we've rolled into a tube, and we will use those to reinforce things like tennis rackets because they're really strong. We also have this one here, which is a buckyball, and you can write the name buckyball, that is exactly right. It's made of 60 carbon atoms joined together in this sphere shape. Now, buckyballs themselves can be used in terms of drug delivery systems and lubricants, so a range of potential uses there. We're now going to consider what actually happens when we change state. So what we find then is when a substance changes from a solid to a liquid, then we're going to be breaking some bonds. And when it changes from a liquid to a gas, the remaining ones are going to break. So what we actually find is the stronger the bond and the more of them there are, then the greater the energy that we've got to transfer from the surroundings in order to break them. i.e., substances with a high melting point have many strong bonds in the solid state. Substances with a high boiling point, many strong bonds in the liquid state. Just go careful to add that little bit of detail about what state the many strong bonds are in if we are talking about changing their state of matter. Now, what we're coming up to next is another property that hopefully we do understand, brittle versus malleable. If something is brittle, that means when you apply a force it's just going to break into little pieces. If it's malleable, you apply a force it's going to bend. Now, the reason that we get that difference is all down to how easily the particles within the structure can slide over each other and change positions in the lattice. So as far as metals go, then metal ions are held in that lattice by those strong metallic bonds, but when we apply a large enough force, the metal ions can just slide over each other. We're not breaking bonds because it's just the attraction between the delocalized electrons and the positive metal ions. So they just move around with the metal ions. Giant covalent structures and our ionic compounds, what we will see here if we apply a large enough force, many bonds are going to break at the same time and it's therefore going to break, it's brittle. Simple molecules and our polymers, those ones tend to be brittle in terms of our simple molecules in the solid state. Polymers, it does depend on the type of polymer, so unlikely to come up as a question because of that, because some of them are flexible, others are rigid. In terms of conducting electricity, as we said, this is all down to do they have charged particles that are free to move. If they have delocalized electrons, then they will conduct electricity. If they have charged particles, so an ion that is free to move, they can conduct electricity. Do bear in mind that when we're looking at this, that means metals will conduct electricity due to the delocalized electrons. Ionic compounds will conduct electricity if they are molten or dissolved. When they are solid, they will not conduct electricity because the ions cannot move. They're held in that fixed position because it's in a solid structure. The others, simple molecules, polymers, giant covalent structures, none of them conduct electricity because of no delocalized electrons there. For those of you doing the triple science, the GCSE chemistry, then we do need to know about nanoparticles. Combined science, you can shut your brains down for about a minute or two. In terms of nanoparticles then, this is a particle that has a size of between 1 nanometer and 100 nanometers across. And remember, 1 nanometer is the same as 1 times 10 to the minus 9 meters. If we talk about a nanoparticulate, this is a material made from those nanoparticles, and the properties from an individual nanoparticle are likely to be different from the properties we find when they're in bulk. So a good example there is titanium dioxide. When it's in bulk, it's white, but when it's on its own, it's transparent. In terms of why nanoparticles are useful, well, they're really small, as we've established, and this means that they've got a very large surface area to volume ratio. So useful as a catalyst because of that very large surface area to volume ratio. They're not perfect though. They are very tiny, which means that they could gain entry to our body by being breathed in, absorbed by the skin, pass through cells, and they're going to take a long time to break down in the environment too. Another downside is that toxic substances may stick to the surface, which are then going to take a long time to break down in the environment. that is the end of C2. So last one that we need to do tonight is C3. First thing, when we're talking about formulas, metals written as the empirical formula, literally just the symbol from the periodic table. We're not going to use numbers because they'd be ridiculously large and they change depending on the amount of metal present. Anything in group 0 exists as an individual atom. Anything in group 7 exists as a diatomic molecule. That means two atoms covalently bonded together. Whenever we're writing it, then that means anything in group 7 must have that little 2 to the bottom right. People mess that up all the time, and therefore balancing of equations always wrong because they've got the formulas wrong, and therefore the balancing is always going to be wrong. Don't forget group 7 diatomic. If we talk about the molecular formula, that shows us the symbols for the elements, so we know which elements are present and how many of each element are present as well. There are some rules that we can learn to make life easier as far as the periodic table goes. Anything in group 1 forms a +1 ion, group 2 +2 ions, group 3 +3 ions, and then as we come across to the other side, group 7 is -1, group 6 -2, and then our group 5 is -3. So not overly likely to get the groups 3 or 5 there, but 6, 7, 1 and 2, make sure you know those rules, because then you know the charge on those ions. We can write formulas from that. There are 5 compound ions that you need to know the formulas for. They are ammonium, hydroxide, nitrate, carbonate and sulfate. If you don't know them, look them up, try and learn them overnight, okay? Because the charges on those could be used to actually write formulas. The key thing when it comes to writing a formula using ions is we've got to make sure that the charges balance. So what we would do then is, if we've got simple one here, okay? Potassium, group 1, single positive, chlorine, group 7, single negative ion. So if we're joining potassium and chlorine together, then what we're going to find is 1 to 1, they cancel out, it's just KCl. If, however, we had magnesium, which is in group 2, then we've got a 2+ ion. If we're still trying to join it to our chloride, what we need to do there is that's going to be 1 magnesium joined to 2 chloride ions, for the simple fact that each chloride has a single negative charge and we've got 2 positives. So we need 2 negative charges to cancel those out. Therefore, Cl2. We do have a law just to remember here, the law of conservation of mass. Atoms cannot be created or destroyed. All that changes is how they're joined together. So that tells us that the mass of our reactants must equal the mass of the products. There are 2 types of equation they could ask you to actually write out on the exam. Foundation folks are more likely to get the word equation. Higher tier folks are going to get the balance symbol equation as a guarantee. So word equations, just use the full names. Don't abbreviate, literally just write the full names down. When you read the question, it will literally give you the answer. It will say something like, magnesium reacts with oxygen to form magnesium oxide. Write the word equation for this. So magnesium plus oxygen, put an arrow in place, magnesium oxide. Balanced symbol equation then is where we need to use the actual symbols and formulas. Then you've got to make sure you've got the same number of each element on the left as you do on the right. And remember, the only place that we can put numbers is in front of the whole formula. You can't just shove a random little number in the middle or at the end. That changes the whole thing. Only in front, and it means you're multiplying that whole formula by 2, 3, whatever. Remember, balancing equations is going to be a 2-mark question when it comes up. The first mark is always for writing the correct formulas. Second mark is the balancing. So even if you are absolutely rubbish at balancing, write down the formulas and you will get 1 of the 2 marks. That's half the marks on that question straight away. The only other bit we could see in there are the state symbols. So they're the little letters in brackets. S is solid, L is liquid, G is gas, and AQ means it's an aqueous solution. So we've dissolved it into a solution. Higher tier folks, so that's combined and triple higher tier. This is for you. Foundation folks, you don't need to know this next bit. We can also be asked to write half equations. Now, a half equation is just a model that shows what happens to one reactant in a chemical reaction. So what we would do is we just focus on the one, like sodium atoms losing electron to become sodium ions. Na makes Na plus and E minus. E minus is our electron, so just remember that. And all you've got to do is just focus on one of them and write it out. When we come on to the ionic equations then, the complete ionic equation shows all of the ions present in the reaction mixture, plus the formulas of any molecular substances or substances in the solid state. Now, what we would do there is they would give you a balanced symbol equation, and then you'd have to write probably a net ionic equation. So if you were to split it all out into the individual ions, what we're then going to find is that there are some that remain the same on the left as they are on the right. Those are the spectator ions. They don't take part in a reaction. We can ignore them when we then write the net ionic equation, because we leave out anything that doesn't change. So just be prepared to write those ionic equations, and I'm not going to go through them in too much detail tonight because you need to see it a bit more. So if you want to go over that, look at the video on the channel. Still higher tier only, we come to the mole. I know it's one of my group's absolute favourite topics. We've only gone through it about 7 times this year. When we are talking about a mole, this is not a small furry creature that burrows underground. This is an amount of a substance that contains the same number of entities as there are atoms in 12 grams of carbon-12. If they give you a nice question to do with moles, then it might be that they're asking you how many atoms are there in 5 moles. So to work that out, all we do is 5 times Avogadro's constant, which is 6.02 times 10 to the power 23. That's the nice question. They could ask you, obviously, to do calculations with moles themselves. And one of the first things that we need to be able to do here then is work out the molar mass. Now, molar mass is quite straightforward. It's the relative formula mass, basically. So where we were looking earlier at some of our formulas here like this, if we're asked to calculate the molar mass, all we need to do, look at the periodic table. Mass of sodium is 23, mass of chlorine is 35.5, add those together, and what we end up with is our actual molar mass, okay? The mass of 1 mole of that substance. So in that case, that would be 58.5, okay? So that's how we start off, working out a molar mass. You need to learn one formula for this, and that is your mass, which is going to be measured in grams, is the molar mass times the amount. So learn this, okay? Mass in grams is your molar mass times the amount. This is what we're going to use time and again in mole calculations. We have basically 4 steps to success in a full mole calculation. They may only ask you to do the first bits, okay? It depends on the style of question they're going to put here. So when we get a question that's asking us to do anything with moles, first thing to do is calculate the molar mass of those substances and write it down. That's usually the first mark on this question. So if you do nothing else, work out the molar mass of each of them just by adding. We can all add. The second step is in the question they will have told you a mass in grams of something. So whatever that mass in grams is, divide it by the molar mass of that same chemical. You now have the amount in moles. Using the balanced symbol equation that will be in the question, you can then work out the proportions. So if you've got 1 mole of something making 2 moles, but actually when you've calculated it you had 3 moles there, you've got to apply that same proportion. So if 1 made 2, 3 will make 6. So we now know the amount in moles of the other chemical. Back to our original one here, so we're going back to this bit again. We now have our molar mass and we've got the amount. Multiply them together, we've got a mass in grams of our unknown. They're the 4 things we need to do. Work out the molar masses, work out the amount of the thing they've given us the mass in grams for, use the balanced equation to work out the amount in moles of the other one, and then molar mass times the amount gives you your final mass there. Still just for the higher tier, you do need to know the difference between the words excess and limiting reactant. If something is in excess, that means we've got more than we need to react with the other reactant. The limiting reactant is the one that's going to run out first, and that determines the amount of product we make. Right, back for everyone. So triple, combined, foundation, higher, absolutely everyone. We're now on to the energetics bit, which is on the advanced listed information for everyone on the triple there. We need to know the difference between endo and exothermic reactions. So first of all, an exothermic reaction is one where the temperature of the reaction mixture increases. We're giving out heat to the surroundings. Think combustion here. Endothermic reactions, that's where the temperature is going to decrease because we're taking in heat from the surroundings. So photosynthesis, electrolysis, thermal decomposition are all endothermic reactions there. In any chemical reaction, we're transferring energy. So we transfer energy from the surroundings to our chemicals to break the bonds in the reactants. Then we transfer energy back to the surroundings when new bonds form. What we need to understand then is how we can represent that in this lovely little diagram called a reaction profile. So they can ask you to draw these, and sometimes it's a sketch, sometimes they're actually going to give you a bit of graph paper, depends on what mood they're in as an examiner. But the principles remain the same. Progress of reaction on the bottom, energy up the side. You're going to have 2 horizontal lines, one for the reactants, one for the products. We're then going to have this little curved line that joins the 2 together. Now, what we do know, I hope, is a reaction profile just shows the energy involved in any given chemical reaction. So those horizontal lines represent the amount of energy stored in either the reactants or the products. We need to know how to label 2 key bits on those diagrams. The first one is going to be the activation energy. Now, activation energy is going to have the bottom of the arrow level with your reactant line and the top of the arrow level with the very top of that little humpy bit there. So same over here, it would just be going to the top of that little humpy bit. Please make sure it's a vertical arrow first of all, and draw it carefully. This kind of sloppy drawing of arrows we sometimes do is going to be throwing away a mark. So what we need to make sure of is that when you do draw that, make sure that the bottom is in line with the reactants and the top is in line with the very top of your actual little hump there. The reason for that is if you don't draw it carefully, they're not giving you the mark. There's only a narrow leeway there. So use a ruler, draw it carefully, vertical arrows only. That's our activation energy. The second one, the energy change, that is the difference between the line for the reactants and the line for the products. Could go up, could go down. It depends on which type of reaction we've got. So what we can see, the bottom of the arrow is going to sit on our reactant line, the top of the arrow dead level with the product line. And again, label that as energy change. Those are the 2 that they could ask you to add on there. Now, in terms of how we would draw endothermic or exothermic reactions, then we can just remember the little pattern here. For an endothermic reaction, reactants are below products. In an exothermic reaction, reactants above the products. So when we're drawing these, you do need to identify, is it endothermic, is it exothermic? Otherwise, your lines for reactant and product could be the wrong way around, okay? So just make sure you identify if it's endothermic, reactants are lower than products. If it's exothermic, reactants are above the products to draw them. Higher tier folks, you could be asked to do a calculation on bond energies. Now, when we talk bond energies, what we're referring to is the energy needed to break 1 mole of a particular bond. You don't have to memorise numbers for this at all. All you've got to be able to do is use the information in the table that they will give you in that question and then calculate it. So to do this, you need to work out what bonds are present. Hopefully, if they give you a question like this, they will be nice, and then they will have actually given you the displayed formulas, like that. If they give you displayed formulas, we need to work out how many of each type of bond are present. So here we've got carbon-hydrogen bonds. We've got 1, 2, 3, 4, 5 of those. We've got 1 carbon-carbon bond, 1 carbon-oxygen bond, and 1 oxygen-hydrogen bond. So we then look up those energies in the table and then add it all together. That gives us the total energy we need to break down, obviously, the bonds in this particular chemical. You do the same for the bonds that form in the products, and then to work out the actual energy change, it's just reactants minus products. What they tend to do with these is they do a question that's normally split into 3 little parts. So the part I, etc. Now, the good thing about that is, even if you can't remember how to do this, if you stick a number in part I, calculate the energy needed to break the bonds in all the reactants, stick a number in part 2, the energy that's going to be released as new bonds form, then use those for part 3, your reactants, part 1, minus your answer to part 2, you get that 3rd mark. Regardless of whether the first 2 bits were right or wrong, that 3rd mark is marked independently. So don't leave those first 2 blank. All you need to do is literally sit there and go, okay, no clue how to work out the energies in those individual bits for the reactants and the products. So you know what? Part 1 I'm going to say is 200. Part 2 I'm going to say is 100. Therefore, for part 3, the energy change, all you've got to do is 200 minus 100, job done, you've got 1 mark there. So a little way to get around if you are sitting there thinking, not a clue how to do this, you can still get 1 of those marks anyway. Now we come on to redox reactions. So this is everyone. So foundation, higher, combined, and triple folks. A redox reaction is where reduction and oxidation happen at the same time. Reduction is loss of oxygen, if we're going with the oxygen version, and oxidation, the gain of oxygen. So what we actually find here is we can see the terms reducing agent and oxidizing agent also used. The thing that is going to be oxidized, i.e. the thing that gains oxygen, is known as the reducing agent, whereas the chemical that is reduced and therefore loses the oxygen is the oxidizing agent. Careful not to mix those up because it's very easy to do. If you're doing higher tier, then you need to know it in terms of electrons, which is where oil rig comes in. So oxidation is the loss of electrons, reduction is the gain of electrons. So all we're really looking at there is, are electrons being lost or are they being gained? If they're lost, it's oxidation. If they're gained, it's reduction. They can ask you to write half equations to show what happens in terms of oxidation and reduction there, but all you're literally doing is adding electrons or taking electrons off. So it's not as bad as it sounds. Back for everyone again, foundation, higher, combined, triple. We're now coming on to pH and neutralization. The basics. Acids, pH less than 7, they go red, orange or yellow with universal indicator, and they release hydrogen ions when dissolved in water. Neutral, pH 7, green with the universal indicator. Alkalis, pH greater than 7, blue or purple with universal indicator, and they will release hydroxide ions when dissolved in water. In terms of how we can measure pH, which for those of you doing foundation chemistry is one of the advanced information practicals, then we can use universal indicator solution. It's rubbish, but we can use it, because universal indicator solution goes different colours based on the pH. But as you probably know from trying to match those colours to that terrible little printout, it's really hard to do. Therefore, to improve how we measure the pH, we use a pH meter or pH probe. The type of reaction that we will have between acids and alkalis is a neutralization. So acid plus base makes a salt and water. What we need to be able to do is name that salt. So the first part of the name of the salt comes from the metal. So just write whatever metal name it is first. The second word of our salt's name comes from the acid. So hydrochloric acid makes a chloride, sulfuric acid a sulfate, nitric acid a nitrate, and phosphoric acid a phosphate. So that gives you the name of your salt. They can ask you how water is formed, and that one quite simply is, in the acid we have hydrogen ions, in the base we have hydroxide ions, and therefore when they react together we make water. So that would be showing how we make our water. You also need to know about the reaction of carbonates and acid. So our general word equation for this is our metal carbonate plus acid makes a salt and water and carbon dioxide. Most carbonates are insoluble in water. The exceptions to this, group 1 carbonates and ammonium carbonate. If they ask you how you can test for carbon dioxide, which technically isn't until paper 2, but we are talking carbon dioxide, so we might as well mention it now. Lime water goes from colourless to cloudy. So that's how we test for carbon dioxide. Lime water goes from colourless to cloudy. Last one of our reactions with our metals and acids is going to be with metals, What we make there is a salt and hydrogen. So again, write down the name of the metal, look at your acid to get the second part, and then just stick plus hydrogen. Gas test for hydrogen, lit splint makes a squeaky pop sound. Higher tier, folks. So this is higher tier triple and higher tier combined. We need to know about concentration. Hopefully we do remember from earlier on tonight, a solution is a solute dissolved in a solvent. The amount of solute within a certain volume is going to tell us the concentration. So if we've got a greater amount of solute in that actual solution, then it's got a greater concentration. Now, what we're going to find is there are going to be two words that we're going to use as far as acids go for higher tier folks. Concentration is one, the amount of solute dissolved in it, and the strength. Now, strength of an acid is all to do with how ionized it is. Weak acids are only partially ionized, and we'll always be able to identify a weak acid because when they're looking at it, there will be the reversible reaction sign there. So they're only partially ionized because some of them are going to reform. Strong acids are fully ionized. All you need to do to explain the difference between the strength of acids, weak, partially ionized, strong, fully ionized. Now, what we find is one of the mathsy questions they could throw in here is looking to see what happens to the pH when we change the concentration of hydrogen ions. And it's a very simple pattern. When the concentration of hydrogen ions increases by a factor of 10, the pH will decrease by 1. So if we were to have a solution of pH 4 and we increase the concentration of hydrogen ions by 100, then obviously that's 2 times 10. So therefore we need to move 2 pH units down. So if we started at 4, 3, 2. Okay, so it ends up at pH 2. For higher tier folks, we still need to know about our pH titration curves. They could ask you the volume required to neutralize, so you end up with a little graph, not drawn proper axes, but you will end up with a little graph like this, where we get that vertical drop, just read off the volume, and that is how much we need in order to neutralize. I would hope they're not going to go into the process of titration on this one. I would expect that more on paper 2. But you do have a basic understanding of titration already from obviously your work on the later units in chemistry. Final bit of C3 is electrolysis, another fan favourite I know. So this is for everyone, foundation, higher, etc. We are looking at electrolysis. Electrolysis, quite simply, is using electricity to split up a chemical. In order to carry this out, we need 2 electrodes, an electrolyte, and some kind of a power supply. If you know nothing else, know the names of the electrodes. The cathode is negative. Think of the cats that are generally just miserable little creatures. They are negative like the cathode. Anode is a positive electrode. So make sure you can remember the names of anode and cathode and whether they're positive or negative. In terms of lines of best fit, I've seen that question there, so I'll just pause a second and just answer that. When you are given a graph to plot in science, literally look at the points. If you can put a ruler on them and virtually all of the points are sitting on that line with your ruler, draw a straight line with a ruler. If you look at it and think, oh, you know what, those ones do, but then it kind of curves at the top, it's not a straight line. Draw a curve. Unlike maths, there are curves that we can use as lines of best fit. So literally look at the points, make your decision based on that. Could be a curve, could be a straight line. Make the decision when you've plotted it. Now, what we then find in terms of our electrolysis, cathode is the negative electrode, anode is the positive electrode. Opposites attract. So in our electrolyte, we have positive ions, we have negative ions. Any of the positive ions are going to be attracted to the cathode because it's negative. Any of the negative ions are attracted to the anode because it's positive. So what we find is that as those little ions are then travelling over to our electrodes, here we can see our positive ions, called cations because they go to the cathode, which is negative, they're going to then become discharged. So here, because they're positive, they gain an electron. On this side, where we've got the anode, the positive electrode, they attract the anions, the negative ions, and at this point, these are going to lose electrons and therefore become neutral atoms again. If we're talking about a binary ionic compound, that contains just two elements. One will be positive, the other will be negative. So whatever the positive thing is, so the metal, will be formed at the cathode. Whatever the negative thing is, that will form at the anode. So just remember, if it's a binary ionic compound, literally, positive ions go to the cathode, negative ions go to the anode, and that's where they form. Do remember though, that will only happen if it is either molten or dissolved. As a solid, they can't move, doesn't happen. We now need to understand the slightly more complex version of the solutions. So that is one of the practicals they've listed on the advanced information for the foundation folks on the chemistry. So in terms of electrolysis of a solution, what we need to remember is the solution means there is water. So because water is present, that means we have got hydrogen ions and hydroxide ions. So just from the water, we have those ions. Then we're also going to have other ions from whatever is dissolved in it. So we may well have copper ions and chloride ions. So what we now have are two positives and two negative ions. Only one will make it to the electrode to be discharged. There is competition. So we have two rules we need to remember. Rule number one, hydrogen is produced at the cathode unless a metal that is less reactive is present. And by less reactive, we mean less reactive than hydrogen. So hydrogen at the cathode unless copper, silver, gold or platinum are there. If they ask you to explain why, because copper, silver, gold or platinum, whichever one it is less reactive than hydrogen is the answer. Rule number two, oxygen is produced at the anode unless an element from group 7 is present. If something from group 7 is present, that's made. If no group 7 present, it's oxygen at the anode. They can give you a little table and ask you just to fill in what's made. As long as you know those two rules, you can get it right every time. So hydrogen at the cathode unless we've got a less reactive metal than hydrogen present, oxygen at the anode unless group 7 are present. When we're looking at electroplating, this is using what we refer to as non-inert electrodes. If something is non-inert, it changes. For the rest of electrolysis, we've been using inert electrodes, unreactive, unchanged at the end. Electroplating, we are deliberately transferring a metal from our electrode to the other side. We're coating something else with metal. So what we actually find is the cathode is whatever we want to coat, the anode is the metal we want to coat it with, and our electrolyte just contains ions of that coating metal. Flip the power supply on, and those metal ions are going to be attracted to the cathode and be deposited on the surface, therefore giving it a little coating there. Do bear in mind that as a result of this, the anode will eventually be used up, because obviously we're moving the ions from the anode to the cathode, so you have to replace it. They could ask you to write half equations for that, but again, it's just adding or losing electrons at that point. Very final thing is looking at how we can purify copper using electrolysis. So the anode is impure copper, the cathode is pure copper, and the electrolyte is copper sulfate solution. Turn on the power. What's going to happen is the copper from the impure anode is going to be attracted to the pure cathode. So the anode gets smaller, the cathode gets bigger. Any of the impurities just sink down to the bottom of the tank as a sludge. So when we then extract the cathode, it is just pure copper. And that is the entirety of C3 and the whole of what can come up in theory on tomorrow's chemistry paper. So we've covered everything from C1, C2, C3. If there are any particular bits that you are still not 100% certain of, then there are the videos on the main channel that cover absolutely everything that you can use. I would suggest having a little flick through just one of the past exam papers on the OCR website just to get a bit of a feel for the kinds of questions that come up, because they don't half repeat themselves on this chemistry. Make sure that when it comes to balancing equations, don't leave it blank if you don't like balancing. Write the formulas if nothing else, okay, because that's one of your 2 marks. And of course, make sure you read the question carefully. While we can't predict exactly what's coming up, if it's anything like the biology paper, then we know that the advanced information gives us a really good idea. There will be a fair number of marks from other sections as well. So do make sure you go over those other bits too. Don't just focus on the advanced information, particularly if you're aiming for those top grades. And then we will be back again with our next live stream before the physics paper, which is after half term. So hopefully, good luck everyone for tomorrow. Enjoy half term, but do still keep revising because exams are not done yet. And I will see you all after the break.